Okay, so let's continue our discussion that we started last time about performance of communication systems in the presence of noise. And we have discussed so far the two situations, one corresponding to transmission at baseband, right, and we found that the signal to noise ratio that you can expect at the output of a baseband system is basically the input signal power as output SNR would be the input signal power divided by the noise power which is present in the message bandwidth, right. SO by NO is equal to S sub I upon NB, and what is NB? It is the total noise power that comes into the system at the output, comes at the output of the system, because this much noise power is present in the message bandwidth. So, the output SNR is essentially what we can say as is the input SNR in the message bandwidth. Whatever is the input SNR in the message bandwidth, that is the output SNR. The input SNR as such is 0, right, because the noise power at the input to the receiver is infinity, but if you consider the noise power in the message bandwidth, that is equal to NB, and that is also the output signal to noise ratio, right. That is the main thing. And when we went from the baseband system to the amplitude modulation systems DSB-SC, we found that the same result still holds, that is the output SNR of an amplitude modulation system is equal to SI by NB, where SI is in both the cases SI is equal to M square, average expected value of M square, right, and NB is the noise bandwidth in the noise power in the message bandwidth. Okay. We will continue this discussion and try to see what happens in the case of SSB, briefly discuss the case of VSB, and then go on to amplitude modulation with carrier, and then amplitude modulation when the demodulation is not done synchronously like what we are discussing so far, but using envelope detector, right. So, we will discuss all these cases before we go to the envelope modulation cases. So, now today we take the case of single sideband modulation, and for the moment we will consider synchronous systems, suppressed carrier systems. So, our model of interest would be, once again you have a message, you first DSP modulate it by multiplying it with the carrier. You will notice that I put different constants in different models. Sometimes I put root 2 cosine omega ct, sometimes I put 2 cosine omega ct. Basically the idea is that I should put a constant in such a manner that the input power to the receiver S sub I in every case is expected value of M square. I just want to keep the same signal power as coming into the receiver input, so as to keep the treatment uniform. It is a matter of scaling, nothing else. It does not affect the results in any way. Even if you did not do this, you would still get the same answers, right. The SNR results will be the same. And after this you will have the SSB filter, right, which will remove one of the two sidebands. That is what you will finally transmit over the channel. The channel once again is going to be assumed to be ideal, and the only effect that is of interest to us is the presence of noise N of t. At the receiver you will have a band pass filter with a center frequency of omega c, but it will remove one of the two sidebands. Oh, sorry, the sidebands are already been, just you are selecting the required carrier frequency. So, selection filter, and then the demodulator, which is again a synchronous system followed by low pass or baseband filter, right, and that is your final output. That is your overall system which you need to analyze, right. So, again as I did in the case of AM, I consider, although this is also really part of the receiver, but let us consider your SI and NI at this point, right. At this point the signal power would be, so this part is your transmitter up to here, this is your channel, and actually this whole thing is a receiver, because it's meaningless to talk about NI here. It is more useful to talk about the signal and noise, input signal and input noise powers at the output of the band pass filter, front end filter of the receiver, because at this point the input noise power is infinity, right. So it's much more meaningful to talk about the input signal power and the input noise power immediately after the band pass filter. That's what we have been doing. So now the usual thing is, okay, we start with the signal. Our transmitted signal is your SSB signal, which we will call, let's call it by x of t, and that we know can be represented in terms of the message signal mt by this. Right, where n hat is the Hilbert transform. Whether it will be plus or minus here will depend on whether you have removed the lower sideband or the upper sideband, right. So that doesn't matter. And you remember the spectrum, just to recap, let's say this is your message spectrum, just for the sake of discussion to remind you, your modulated signal would have a spectrum like that. Right. That's if you are considering lower sidebands. If you are considering the upper sidebands, it will be the other way around, right. So corresponding to this message spectrum, you have this. So what is the power of the message signal? That is, what is the power of 2 mt cosine omega ct that you have here? What will be the power here? It will be 2 m square bar, isn't it? If I were to compute these powers, various powers, so let's look at power of 2 mt cosine omega ct, right. This will be basically integral of the square of this, which will be equal to 2 m square t bar, right. That's straightforward. When you remove one of the sidebands, how much power you are left with? Half of this. So therefore, what is the input signal power that is coming in here? Once again m square bar, and that is the reason why I am multiplying with 2 here. Basically the idea is to normalize S sub I in every case to equal to m square bar if it is possible, right, just for the sake of convenience. So therefore we can say that S sub I, the power at the input to the receiver, input to demodulator I should say, not to receiver, is equal to m square t bar. Simply call it m square bar. So at the demodulator input you have, if I call this signal at the demodulator input as YIT, can we write an expression for this signal YIT? What is the signal that is coming here? It is a transmitted signal, which is the SSB signal, which has its representation in terms of the Hilbert transform, plus the noise. And what kind of noise is present here? Band pass noise, narrow band noise, which again one can write in quadrature form, right. So therefore the expression for YIT, like I did for the AM case, would become mt cosine omega ct plus m hat t sine omega ct. This is the signal part, plus using the same notation that we used last time, n sub ct cosine omega ct plus n sub st sine omega ct. This is the noise part. This is a quadrature representation of the band pass noise that is coming out of the band pass filter at the receiver. So, this signal on the whole will have an in phase component which is MT plus MCT into cosine omega CT plus a quadrature part which is M hat T plus MT into sine omega CT, right. That is the input to the demodulator. What will be the output of the demodulator after the low pass filtering? We are multiplying this with 2 cosine omega CT, right. Obviously, this quadrature component will produce no output. The only output will be due to this, and it will be simply MT plus NCT, right. So, output of the demodulator, if I call it Y sub OT, so I am calling this signal Y sub OT, right. Then Y sub OT essentially will be MT plus NCT, because when you multiply with 2 cosine omega CT, you will get 2 cosine square omega CT, which is equal to 1 plus cos 2 omega CT, and the only part that will be left after low pass filtering will be MT plus NCT, right. This is the signal part of the output, this is the noise part of the output. So, what is the output signal power? What is S sub O? Once again M square bar, and what is, which is equal to S sub I, right. So, output signal power once again as in the earlier cases is equal to S sub I, and what is the noise power? It is the expected value of NC square, which once again is equal to expected value of N square, if you remember, and that is equal to once again how much? What is the bandwidth of this band pass noise? It is not 2B, it is simply B, because this band pass filter has to have bandwidth only of B hertz, not 2B hertz. In the case of AM it was 2B. So, it is N by 2 into B plus N by 2 into B for the negative part, negative frequency part. Is that clear to all of you? So, the total output noise power once again is equal to NB. So, nothing has changed. So, output output SNR once again is M square bar upon NB, which if you were to write in terms of inputs message power, which is S sub I, and noise power in the, this is again the noise power in the message bandwidth. Noise power spectral density is 1 by 2, right. The amount of noise power in the spectral in the bandwidth of the message will be N by 2 into 2B, because the baseband signal has a bandwidth of B, or on the frequency axis from minus B to plus B, N by 2 into 2B gives you the noise power in the message bandwidth. So, once again output SNR is the same as the input SNR. So, this is very interesting, and of course, it is intuitively to be expected that as far as the noise performance is concerned, these systems would they have no reason to differ from each other, right. So, essentially when you go from let us say baseband to AM with double sideband and AM with single sideband, the considerations are different. It is not because of better performance in noise, right. When you go from double sideband to single sideband, it is because, it is not because you are likely to get superior noise performance, right. It is simply to save bandwidth, right. Incidentally, as far as bandwidth is concerned, in some sense DSP and SSP are same, because in DSP, although the bandwidth is twice, you know that by using quadrature modulation I can transmit 2 messages instead of 1. So, really they are practically, for all practical purposes, they are equivalent if we can exploit that in a particular application. Otherwise, of course, SSP. So, once again this is equal to gamma, right. So, the figure of merit so far for all the systems remains the same, equal to gamma, right. Now, when you go from SSB to VSP, suppress carrier once again and carry out synchronous demodulation, using the same arguments that we have used here. If you remember, we have a very similar quadrature representation for the VSP signal, except that this is no longer the Fourier transform. It is a signal obtained by passing MT through an appropriate filter, right? What we call the VSP filter, right? However, the details are a little complicated, not too much. I'll leave that as an exercise for you to do yourself and show that in this case also the output SNR is approximately equal to gamma, is nearly the same as gamma, right? So whether it is DSBSC, whether it is SSB, whether it is VSP, the performance of the system after synchronous demodulation is the same, right? Same as that of the baseband system. So there is really you are not achieving anything in terms of SNR performance when you are doing amplitude modulation. That's the message. That's the moral of the story. Okay, that's what you need to understand. Okay, maybe at this stage I could take up a very simple example. This is an example from the book itself, but still it's worthwhile doing it, right? Just to see what kind of calculations you may actually have to do to calculate the output SNR, right? Let's say we have a message which is which has a uniform power spectral density. We will assume the message, as we have said earlier, message is being modeled as a random waveform, right? So it is defined in terms of its power spectral density function in the frequency domain, right? And let's say it has a uniform power spectral density function over its bandwidth, which is assumed to be 4 kilohertz, right? That means the power spectral density function is flat, extending from minus 4 kilohertz to plus 4 kilohertz. That's what it means. Let's say we are working with a DSBSC system. Okay, carrier frequency is 500 kilohertz. Just some figures. And let's say noise is not white, but colored, which means it has a non-flat power spectral density function, and that is given by 1 by omega square plus a square. Okay, so we are assuming the noise power spectral density function to be something like that, right? Which is what will happen if white noise were to be first passed through a filter with this transfer function, right? So it's some kind of a filtered noise. It doesn't matter, just for the sake of argument, and the value of A is 10 to the power 6 pi, just some numerical values to give you some feel. And this makes sense because if your carrier frequency is 500 kilohertz, it is noise up to about that bandwidth which is really going to play a role, if at all. Okay, so and the final data that is given to us is that the useful signal power at the receiver is equal to 1 microwatt. That is, at the receiver input, the signal power that you receive is about 1 microwatt, right? And our objective is to determine the output SNR from these figures. Of the receiver. So how will we do that? So we are transmitting the DSBSC signal, which is MT cosine omega CT, right? It will get attenuated by some scaling factor. Let's say the received signal is k MT cosine omega CT, right? So what will be the demodulator input now? It will be k MT cosine omega CT plus NCT. I am talking about YIT. Y sub IT is a notation for the signal which is present at the input to the demodulator, right? It will have the modulating signal plus the noise, right? As the input to the demodulator. So we will multiply this with the 2 cosine omega ct, right? And the demodulator output would be, if I multiply this with, that's your demodulation operation, followed by low pass filtering. If you do that, your output would be, so you don't have to remember anything, you can always do it from basics, right? It will be kmt plus nct, right? This is your S naught t, the signal part of the output, this is the noise part of the output, right? So your output power is k square m square bar in this case, and that is what is given to be. Now this is not what is given to be 1 microwatt. One has to be a little careful there. What is given to be 1 microwatt is the input power at the receiver, right? The signal power that is incident to the receiver. What is the signal which is incident to the receiver? It is not kmt, it is kmt cosine omega ct, right? What is the power of this? What is the power of this? K square m square bar upon 2. So this is given to be 1 microwatt, right? This is 10 to the power minus 6 watts, which means k square m square bar is 2 into 10 to the power minus 6 watts. So S naught is 2 into 10 to the power minus 6 watts. So output signal power is known. The only thing left to do is to calculate the output noise power, right? So what is the output noise power? Which is equal to the power in NC, this in phase component of noise, it is NC square bar, which is the same thing as M square bar. So basically it is the noise and it is the power in this narrowband noise of bandwidth 2B, right? Now this is not a flat power spectrum, so I can't simply multiply n by 2 into 2B, which is what I have done in the previous examples, right? What you will have to do is integrate the noise spectrum, right, between Fc minus B to Fc plus B and take twice of that, right? This is for the positive frequency part, and there will be corresponding for the negative frequency part. So that's why I am doubling it up. So you have to calculate this integral. Fc here is 500 kilohertz, B is 4 kilohertz. So this becomes 496 kilohertz here, and this becomes 504 kilohertz here. So you have to take this expression for the noise power spectral density function and integrate it over this domain, and if you were to do that, the numerical answer that you will get, let me write it here itself, will turn out to be 8.25 into 10 to the power minus 10 watts. Okay. And if you were to now calculate the signal to noise power ratio, that turns out to be 2.42 to 10 to the power 3, which is of the order of 33.8 decibels. Okay. So I thought we will go through one sample calculation to get this idea of how do you actually calculate the signal to noise ratio and what is the order of values that you can expect. Right? Yes, please.
So what is the use of saying the MT as a uniform PSC?
This is just to simplify, because otherwise the noise power calculation, I don't think we are using it directly, except that the filters will be assumed to be ideal low pass filters. Right? You can assume the filters to be ideal low pass filters. Otherwise, the filters need not be ideal low pass filters. In fact, if you are, this is let me spend a couple of minutes on this question since it has been asked, just to give some feel for some of the things that, some of the details which we are not discussing here. Right? by saying that the signal has this kind of a spectrum, right, basically what we are saying is we can use the final low pass filter after demodulation to be a filter of this kind of shape. Suppose I were to tell you that the power spectral density within this bandwidth is distributed like that. The message spectrum is not like this but like this. Then using an ideal low pass filter as a final baseband filter is not the best thing one can do. Can you appreciate why? Because I can see that different frequency components have different importance for the signal, right. In the signal there are different importance to different frequency components. So why should I allow so much noise to pass through, give the same gain to all frequencies between -4 to 4, because although my signal is going to be weak, I am multiplying by a large amplitude unnecessarily, which will simply amplify the noise components without giving me any benefit about the signal, right, although there is no signal present. So the best filter to use then will not be an ideal low pass filter, but some kind of a different transfer function which gives higher weightage to those frequency components where the signal to noise ratio is good, and lower weightage to those frequency components where the signal to noise ratio is poor, right.
Pre-emphasizes the pre-user.
Not the pre-emphasis. This is as if the best filter to use at the final output would have to do with the kind of signal to noise ratio distribution you have across the bandwidth, right. So that is the only significance of that assumption, that we can use this as we can assume that the final baseband filter is an ideal low pass filter, right. Otherwise, if it is not that, the best filter is not an ideal low pass filter. However, we are not going into those issues because those issues are really dealt with in area called as estimation theory. How do you estimate the signal with any kind of spectrum in the presence of noise with any kind of spectrum is a much more difficult problem and requires some formal background which we do not have at this stage. Okay? Thank you. Good question. Okay. What is the next system we should consider? Amplitude modulation with carrier, and see how things change. Again, you can intuitively expect how things should change. Can you intuitively expect something? Okay, you have two cases there. One, when we take amplitude modulation with carrier and demodulate synchronously, and that is the case we will take first. And the second situation could be when we demodulate using the envelope detector, right. So let us consider AM. When I say AM here, I am talking about AM with carrier. That is not suppressed carrier, right. And let us talk about synchronous demodulation first. Either coherent or synchronous demodulation. So, what is the kind of signal that you are transmitting now? Let me not draw the diagram. The diagram is more or less the same, except that you also have the carrier. So, what is the kind of received signal? I think directly come to the received signal now. You can say root 2, there is a carrier component and there is a message modulated message component. Excuse me. Alright. So, I have this is a transmitted signal, AM signal with carrier. The factor of root 2 or factor of 2 that I might include is just to make sure that the final SI, the message power part is the same. There is no other requirement. So, what is the received message power in this case? It will be root 2 square A plus MT square upon 2, right. So, it makes it A plus MT square like that, which you can expand as A square plus M square bar plus 2A MT, right. I just expanded that, and if you assume that the message is 0 mean, right, it is A square plus M square. means the message has no DC component. Okay, so this is your expression for the input power. Now this is different, right? It is no longer m square bar because you are also transmitting some carrier, right? What is your demodulation process? Once again, this root 2 into a plus mt that you are receiving, you are going to multiply this with, let us say, root 2 cosine omega ct, and the result will be low pass filter. These are the operations you are going to do for demodulation. Multiply the root 2 cosine omega ct followed by low pass filtering. What will result? What will the demodulated output? No, the A part is not message, right? So the message part is only empty, right? So really speaking, you will get empty as far as the signal part is concerned, right? So your output signal power will once again be equal to m square bar, and as far as the noise is concerned, there is no difference, right? So what can I say about S naught by N naught? It is m square bar upon NB, and now I must express it in terms of signal to noise ratio of the input, because that is our benchmark, right? Our benchmark is in terms of SI by NB. Suppose I were to do that, I can rewrite this as m square bar upon m square bar plus a square, which is your SI. I am dividing it by SI basically and multiplying it with SI. These two will cancel off and you will be left with this only upon NB, right? So this is your result. Into gamma. So what do you find? That the output SNR is now smaller, and that is expected because when you are transmitting an AM signal with carrier, not the entire input power, entire useful input power is useful in terms of the message, right? Part of this input power is carrier and part of this input power is message, right? So that's therefore you lose in terms of performance, right? That is to get the same SNR as the other systems, you will have to have a higher value of gamma because of this attenuation factor that is coming into the process. Is that okay? So obviously in terms of SNR performance, AM would be inferior, AM with carrier would be inferior. Have you all understood this? Good. Let's continue this discussion a little further to appreciate how much more power will be required in typical situations as compared to AM with carrier, AM without carrier. Let's consider the case where, let's say, the maximum value of your message is, the peak value is m sub p. Why that is important? Because if you remember, your A plus mt, for this to be well, of course for synchronous demodulation that is not very important, but typically you would keep your A plus mt to be positive, right? Although for synchronous demodulation that is not a requirement, it does not have to be so, but that is the usual condition, because we want that. Basically what does it mean? That A will then be greater than or equal to m sub p, because if you have a negative peak, for example, A plus mt should still be positive. So the value of A should be greater than or equal to m sub p. So for maximum SNR, what should we do? To obtain the maximum possible SNR, we should choose A equal to the largest possible value. Is it? Because that will give you 100% modulation. A is equal to MP, and your S naught by N naught maximum would be m square bar upon m square bar plus mp square upon m square into gamma. So, that is in terms of the peak value. Is that okay? A must be greater than or equal to NB. Since A occurs in the denominator, you must choose the smallest possible value of A, right? And the smallest possible value of A is NP. That is what I have done. So, this is some kind of an expression for the output SNR in terms of only the message properties, right? Nothing else. And now, if you were to take some typical example, okay, there is one more way in which you can write this. Before I take that, you can write this as 1 by 1 plus mp square by m square by. This actually there is no bar here, right? This is just the peak value. Sorry for that. Okay. Now, what will be the typical value of this ratio mp square by m square bar? What will be the typical value of this? Would be less than 1 or more than 1? More than 1, because mp denotes the peak value, m square bar is the mean square value. This is the square of the peak value, this is the square of the mean, this is the mean square value, right? So, obviously, the peak square to the average, peak to average ratio is typically going to be greater than or equal to 1, right? So, this obviously means that this attenuation factor, this factor by which the effective SNR gets reduced is going to be, so this is going to be less than or equal to gamma by 2. This is of course a very rough bound, but what this bound tells you is that there is at least a 3 dB disadvantage, a 3 dB cost associated with use of carrier than not using the carrier. Then at least 3 dB, isn't it? That is, I must require at least 3 dB more power, twice as much power for transmission. Gamma should be at least twice as much as earlier, so as to get the same value of the SN. Right? Typical situations will be actually more than 3 dB, because this is, very rarely you will have mp square by m square bar equal to 1. It will be typically much greater than 1, at least somewhat greater than 1. So, depending on the actual value of this ratio, the actual SNR reduction or the SNR cost or the power cost associated with use of AM with carrier is more than 3 dB, right. Typical figures are more like 6 dB to 9 dB, right. There is a 6 dB to 9 dB loss in power efficiency. This is more typical. 3 dB is absolutely minimum value. For example, suppose your modulating message signal was a sinusoid, just for the sake of discussion. Suppose your MT was a sinusoid. What is the peak to RMS value for that? Root 2. Peak to RMS is root 2. So, what is MP square by M square bar? It is 2, right. So, instead of 1 it is 2. So, what will be the value of S by N naught now? It will be 1 by 3 gamma, right. So, which is about 6 dB, actually 4.77 dB less, right. So, this is, if you were to talk in terms of dBs, right, this in dB would be gamma minus about 4.77 dB. So, you require 4.77 more dB more SNR to get the same output SNR at the input. At the input you require this much more to get the same output SNR. Okay. So, while 3 dB is a minimum, it will actually range somewhere between 6 to 9 dB. Any questions so far? So, what we have learnt is that there is a cost associated with performance, power efficiency, etc., when you transmit with carrier. Of course, the reason why we do it is because it is simpler to demodulate, right. We do not actually have to do synchronous demodulation, and that brings us to the next question. This power loss or this power efficiency that we have calculated as output SNR that we have calculated is for the situation where the demodulation is synchronous. but actually we transmit carrier so as to get the simplicity of demodulation, not to have to use synchronous demodulation. So, the next question is, would the envelope detector give you the same performance as the synchronous detector does, as the coherent detector does, right? That is the next question that we need to look at. So, let us look at AM with envelope detection. The process is very similar. Start with the received signal. Everywhere more or less the same steps are involved. So, once again let us say it is A plus MT into cosine omega CT. Do not get confused by the fact that sometimes I use some factor and sometimes I do not use some factor. It would make absolutely no difference to the final result, right. Please be clear about that. So, how should we proceed? Before I actually proceed, let me see whether you can give me an idea of how we should proceed now to calculate the output, because we now done some sample calculations. Let us discuss very briefly what should be the process now, because we are not at the receiver, we are not going to multiply with root 2 cosine omega CT or cosine 2 cosine omega CT, right. We have to do envelope detection. So, what kind of mathematics we should do now? You think?
So some kind of filter.
Some kind of filter. No, what is the actual operation we do in envelope detection? That's what we do.
Differentiation. We put it in the capacitor equation or the equations of the capacitor. There is a voltage, power loss and
He's saying that you look at the resistor, the capacitor, you know, that's a very involved.
draw the waveform.
Mathematically, what are we doing? We are trying to produce an output which is proportional to the envelope of the input, and you know how to write a mathematical expression for the envelope, isn't it? That's what we should do. That may not be the actual thing, but it will be very close to the actual thing, because that's what the envelope detector is actually supposed to do, produce an output which is proportional to the instantaneous envelope. So, if I write down an expression, mathematical expression for the envelope, in this case, that's what.
So that will be the amplitude only, A plus M.
No, but that's not what you are going to receive. This is the received signal part. The actual received signal Y sub IT will have the signal part plus the noise part, and it is the envelope of the signal plus noise which will dictate the output. Is it clear? So, we need to look at that, right. So, input to the demodulator, the input to demodulator is Y sub IT, which is A plus MT into cosine omega CT plus the narrowband noise that is coming along, right. Remember, when I say input of the demodulator, we are considering this is the output of the band pass filter, which is the front end, the first stage of the receiver. The receiver will always be associated with a band pass filter to pick up your desired signal. It will have a bandwidth of B or 2B. In this case, it will have a bandwidth of 2B, right. Right. This is A plus MT plus N sub IT. You can write in terms of quadrature representation. The in-phase component of that is N sub CT. This entire thing into cosine omega CT plus NST sine omega CT. Okay. So, once again let us write down the expression for SI. SI is the same as before, except that since I do not have a factor of root 2, I will write A square plus M square bar upon 2. Right? If I have that factor of root 2, then I did not have this factor. As I said, it will not make any difference whether you start with the factor or do not start with the factor, things will get modified accordingly, right. So, that is your expression for the input signal power. This YIT now I can write as equal to the envelope of this signal, let me call it E sub I t. What is the expression we have been using now so far, E or R? It doesn't matter, let us call it E in this case, cosine omega c t plus theta t, right. I can always write this trigonometric expression in terms of this trigonometric expression, right, where E sub I t, which denotes the envelope, will be given by square root of a plus m t plus n c t whole square plus n s square t, right, and there will be some theta t, which you can write as tan inverse of n s upon this entire thing, but that is of no interest to us. So, I am not even going to write it down, because finally the envelope detector will produce an output which is proportional to the envelope. So, this is the main thing of interest to us, and this contains, as you can see, the signal part as well as some noise part, but there is a non-linear dependence now, right, and that is what makes the situation in general a little more difficult. And to consider, to simplify the situation, one makes some assumptions, and the usual assumption that we make to do the initial analysis is the small noise assumption, right. So, let us make a small noise assumption. Basically, what is the small noise assumption? That is essentially to say that the signal power at the input, this is much greater than the noise power at the input. That is, the signal is much stronger than the noise.
Is this divided into hearing?
Typically, yes, and if particularly it depends on the kind of situations you are working with. In broadcast applications, it is justified, right, because you have to maintain a good signal to noise ratio, right. In many other applications, it may not be justified. In that case, you will have to make the other opposite, I mean, to simplify things, you may have to make the opposite assumption, that the signal is much stronger than noise, right. That also can be done. Otherwise, you have to write a general expression which is very complicated, right. So, just to simplify things and to gain some kind of understanding, it is convenient to make these assumptions. So, small noise assumption will imply here that A plus mt is much greater than n sub I t for all values of time, right. Although NIT is actually random, so making this kind of a statement is a kind of loose statement, but I think it is convenient to at this stage to make this kind of a loose statement. This will of course also imply that A plus mt will be much greater than either NCT or n sub st for all time. If that happens, look at the envelope expression. Obviously, this term will be dominated by this square plus this square will be dominated by the square of the first term, and we can ignore the contribution of the second term, right. So, what are we left with? So, your demodulator output or the envelope E sub I t under this assumption would be approximately equal to A plus mt plus NCT, right, and of course, this will be blocked by some capacitor. You are not interested in this A, you are only interested in mt. The useful signal power of the output will then become m square. The useful and corresponding noise power will be equal to NC square, which is once again, in this case, how much will it be? Remember, this is an AM signal whose bandwidth is 2B, right, from Fc minus B to Fc plus B. So, n by 2 into 2B is NB, corresponding negative part is NB, total output noise power is 2 NB, right. So, same picture as before, therefore, S naught by N naught. So, nothing has changed, things are absolutely the same as before, right. This is, you can write this as m square bar upon right. Okay, because your SI is, if you remember, I have to, your SI is this. Okay, so if you take out this factor of 2, this finally disappears. You are left with the same expression as before, isn't it? So your output SNR, now this is very important to appreciate. Although the expression is same, but there is a very important message here. That is same as before. What I mean by same as before, what I mean by this is that the output SNR is exactly the same that we had for the case of synchronous demodulation. That is expression for the output SNR. Now what is the difference? Whereas for the synchronous demodulation, this expression is valid irrespective of the input SNR, right? For the case of envelope detector, this expression is valid only when input SNR is sufficiently large, right? Is it clear? That we don't know, we have to find. At least this, all we are saying is this assumption that we made in the analysis is not valid, and therefore this expression will not be valid. We will not be able to calculate the output SNR using this expression. That's all we can say. Whether it will be worse or better, we don't know, right? We have to find out. But so basically what we are saying is in high SNR situations, it hardly matters. We don't lose any further in terms of power efficiency if you were to use the envelope detector rather than the synchronous detector, right? Is it clear? For high SNR situations, there is no loss. So envelope, you can just go ahead and use the envelope detector without even thinking twice, because you will not lose any performance. Yes, as you are rightly pointing out, for low SNR situation, the envelope detector actually will work worse, right? And one has to be a little more careful. Although it's not obvious, but that's the next thing we are going to take up. So the second situation we can analyze by to simplify things is when the motivation is the same. We somehow want to simplify the expression for the envelope, right? So one way of simplifying it is by assuming that this is a much larger term than this. The other way is assume that noise is much larger than the signal, right? And then again we can do things slightly differently. So the large noise case. So we will consider both the situations. And what do we mean by large noise case? What we are saying is the opposite of what we have said earlier, that your noise amplitude most of the time is much greater than A plus MT. The received signal is much weaker than the noise, right? For Alt, which essentially would imply that both NCT and NST are much greater than A plus MT. Now what can we say about the envelope? So EIT would be approximately equal to, best thing is to expand this square term, we will get A square plus M square plus NC square plus cross terms and things like that, and the significant terms there would be NC square T, because that is large, plus NS square T plus 2 NCT into A plus MT. Right? Okay, I'll just write this expression completely and then we'll do the discussion next time. So let me write this again. We can write this as, if I were to divide this, now just think about it. Can I give some interpretation to this quantity? This is the envelope of the noise process itself alone, because noise is NCT cosine omega CT plus NST into sine omega CT. So you can think of this as the envelope of the noise process. So I can rewrite this as En square t, right, etc. So I can write this as, if I take this ENT outside this square root sign, this will become 1 plus 2 into a plus mt upon ENT and cosine theta nt. Okay, you think about that. We'll start from this expression now. What I am saying is we can rewrite this in this form. Theta nt is tan inverse of ns by nc. We'll start from this expression next time. Thank you very much.